So, yeah, John, please go ahead.
Thanks, George. Okay, it's great to be here. So first I'll tell you what the agenda is for all of my talks today and in subsequent days. So originally it was going to be split between me and my advisor, Peter Beal, but unfortunately he couldn't make it. So I'll be teaching all of these sessions. No one wants to listen to me talk for 3 hours straight, so I thought it would be a good idea to break up this morning session and have some problems that you can solve after I talk for a while. So first, I'm going to start off by giving an overview of reinforcement learning and deep RL, and then I'm going to talk about the simplest kind of algorithm, derivative-free optimization algorithms. Then there are some exercises where you can try implementing one of these algorithms. And if you don't want to do that, there's another exercise that doesn't involve any coding. Then at the end of the session today, I'll start talking about policy gradient methods. Then on Monday, I'll talk about value functions and Bellman equations. If you don't know what those are, that's okay. And last, I'll talk about active break methods, which are policy gradient methods that also use value functions for variance reduction. So I would say that overall, the topic of this, the topic of all these talks will be, it'll be deep RL with a focus on policy gradient methods and in general policy optimization. And there are other approaches to reinforcement learning, but I feel like this is one that isn't shown that frequently. I mean, usually you see methods that are more based on dynamic programming, which I'll talk about a little later. Okay, and all of the course materials, including these PDF slides, are available on that URL, so you might want to write that down. And also the exercises are available there. Can everyone see that? All right. Okay, so first question is, what is reinforcement learning? So in a broad sense, it's the branch of machine learning concerned with taking sequences of actions, and sometimes it's called control, sometimes decision making, and so forth. And usually the two main characters are the agent and the environment. Every time step, the agent outputs an action, and every time step, the environment returns an observation and a reward in general, or possibly the state of the system and the reward. So usually reinforcement learning is described in these terms where you have an agent interacting with the previously unknown environment and trying to maximize this cumulative reward. That should say observation and reward. Okay, so what are some examples of reinforcement learning, of areas where you might want to apply reinforcement learning, that is? So one area is robotics. That's the one I'll be using the most as a motivating example in these lectures. So in robotics, the observations might be images from a camera and the joint angles of the robot. The actions would be the joint torques. That's a very low-level kind of control, but if you want to take it to the extreme, those would be the actions. And the rewards would obviously depend on the task. For example, if you're trying to get the robot to walk successfully, so if you're doing locomotion, then you would say the reward function would encourage it to stay upright and balanced and navigate to target locations. But who knows, there are all sorts of possibilities. Okay, so another area where reinforcement learning has been applied for a long time falls under the umbrella of operations research. So in that field, they look at problems, well, a variety of different problems that sort of come up in business management or any kind any kind of management application. So one is inventory management. So you could imagine you have a store and you have to decide how much to buy of all of your goods, because if you run out, then you're not going to sell any more of it, and your customers will be upset. But if you buy too much stock, then you might lose money because you have to throw it out later, or you're wasting your capital. So you might have observations that are your current inventory levels, actions that are how many of each item to purchase, and rewards would be your profits. There's another set of problems that are like resource allocation. So queuing problems are really well studied in this field, and in those problems you have a set of customers that you need to provide some kind of service to, and so that's your queue, and you need to decide what to do with them. And then last, there are problems that sort of are called routing problems, where you have, for example, you would have a fleet of trucks, and you have to decide which trucks to assign to which cargo. So you could look at this as a reinforcement learning, or as a sequential decision-making problem, and you can learn how to solve it better with reinforcement learning. Lastly, reinforcement learning has been applied to games, and two-player games are actually a different kind of optimization problem from the main, the type of problems we'll be mostly considering, which are called Markov decision processes. So this kind of problem is different because it's really a minimax problem, where I'm optimizing my strategy given that someone else is optimizing their strategy. But still, it's usually studied in the general field of reinforcement learning. So there are various different types of games. So you can have complete information games where you see everything, nothing's hidden, and where it's deterministic. So Go is an example of that, and you probably all know about AlphaGo, where DeepMind got a Go playing program to beat the world champion recently. Backgammon that's a complete information game where you have to roll dice, so it's stochastic. And actually, I would say the first result of deep reinforcement learning was Gerald Tesoro's. He trained a neural network to play backgammon back in the late 80s or early 90s, and it ended up being either the best, beating the world champion, or at least playing at a professional level. So that was a pioneering piece of work, and he used classic, what's called TD methods, which I'll discuss later. That's why it's called TD gammon. Then you could have other kinds of games like incomplete information, deterministic, or a game like poker where information is hidden and it's stochastic. Okay, so here I'm showing a sort of taxonomy of different approaches to reinforcement learning. So there's sort of two overall, two quite different strategies for deriving reinforcement learning algorithms. One is to optimize policies, and the other is dynamic programming. So what does that mean? A policy is the function that takes in the observations or the state of the system, and it outputs actions. So policy optimization approaches just look at this as an optimization problem, where you're trying to optimize your expected reward, and you have some parameters of your policy, and you just have an optimization problem. You're trying to optimize some expectation, and so given that you're just looking at this as an optimization problem, there are two different ways that you could go about it. One way is to say that we've got this parameter vector of the policy, and let's just ignore all the structure of the problem and say I can take a parameter and measure, get a noisy estimate of how good it is, and then try to move towards the part of parameter space where where we're getting better performance. So that's derivative-free optimization or evolutionary algorithms. So these methods sort of look at the whole, they look at the whole process for generating rewards as a black box that takes in the policy parameter and outputs a noisy performance number. And these methods are actually the simplest to implement, and they actually work surprisingly well. And today, after this introductory material, I'll talk about a simple algorithm of this sort. The other approach is policy gradient methods, where you actually try to measure the gradient of the performance with respect to the parameters of the policy. So these methods are a little bit more complicated to get working, but they can. But when you have a very large number of parameters, they can actually optimize those kind of policies. So they scale better with the number of parameters. Okay, then so that's that'll be the focus of these lectures, and these methods are actually very good and very effective. Okay, so then there's another totally different approach to reinforcement learning, or to at least to deriving reinforcement learning algorithms, and that's dynamic programming or approximate dynamic programming. And this is actually what most reinforcement learning courses and textbooks start with. So it's actually so that's why it's a little unusual that I'm going to focus on this stuff. But okay, so dynamic programming. If you have in certain cases, you can exactly solve control problems using dynamic programming, so you can come up with these algorithms that exactly solve problems under certain circumstances, and then you can say, okay, what if we're in a slightly harder setting? Do these algorithms still work? And it turns out that you have to modify them in certain ways. So policy iteration and value iteration are these two algorithms that will exactly solve markup decision processes and find the optimal policy. But they only work if you have discrete state spaces and action spaces. So if you have if these spaces are finite sets, and oops. Okay, I'll talk in a little more detail later, so if you don't know what I'm talking about, that's fine. I'm going to move on in a sec. But the point is these algorithms can exactly solve these problems, and then when you move on to real problems that you actually care about, they don't quite work, so you have to do approximate versions of these algorithms. And so there's a whole field that tries to develop approximate dynamic programming algorithms. And Q-learning is one quite popular and successful method in this category. And you can do Q-learning with function approximation, for example, with neural networks as function approximators. But these methods are a little harder to analyze because it's not just optimization; it's some kind of iterative algorithm where it's hard to understand exactly what's happening. Okay, and then lastly, there are these actor-critic methods, which are policy gradient methods, but they also they use value functions, which are sort of the main objects considered in dynamic programming. So you've got value functions from dynamic programming, and you use them to help out policy gradient methods. And these are sort of these methods when they work, can be really scalable and can solve a lot of hard problems. And when I get into these methods in the third lecture, I'll show some pretty cool examples of like learning how to get a 3D robot to walk. So you can solve pretty large-scale problems with these methods. Okay, so what is deep reinforcement learning? So it's just reinforcement learning using nonlinear function approximators, and function approximators where you don't make a lot of assumptions about the form of the function approximator. So people have been, if you look at any reinforcement learning textbook, it'll probably talk about using linear function approximators or function approximators that are linear in parameters. And there are certain methods that are like, they're like least squares methods that'll just work if you have linear function approximators. So I would say that I would define deep RL as a set of methods that don't make any of those assumptions, where you can just do, where at any given time in the algorithm, you're solving some kind of optimization problem using gradient descent. Okay, and here's a semi-serious alternative definition. So you could say that if you look at the cerebral cortex, you could say there's a lot of different parts of the brain that do different things, and the back of the brain is the visual cortex and is involved with vision. So you could say that the back of the brain is doing. This is sort of the set of functions that computer vision is trying to solve, and then the front of the brain is known to have motor areas. So it's known to be involved in motor control and also decision making and so forth. So you could say that deep reinforcement learning is trying to do whatever the front of the brain does. And I like this definition because you can come up with a formalization of optimal control. Like you can say, we want to find optimal policies for Markov decision processes. But that's not necessarily exactly the right problem. You might want to do all sorts of other things, like learning from demonstration and so forth. And so that's why I think it's useful to have a more general picture that there are a lot of different kinds of functionality that you want related to controlling things and making decisions. And that's sort of what deep RL is about. Okay, so now time for some actual technical material. So I'm going to start off by just defining a Markov decision process. So a Markov decision process is defined by a tuple of several things. Here are three things. The state, so S is a state space, A is the action space, and P is this transition probability distribution. So this tells you the probability of the reward, and that's just a scalar, that's just a real number, and the next state, that's also in the state space, given the current state and the action. Okay, and depending on the problem setting, you might also have to define some other objects, which are sometimes called part of the MDP. So one extra object that you sometimes need to define is the initial state distribution. And another thing that people sometimes define is this gamma, this discount factor. That's just a real number between 0 and 1. And that tells you that you care less about stuff far in the future than near in the future, than near. So we're actually not going to talk about discount factors as part of the definition of the problem. We're going to talk about it as part of the algorithm, and it'll come in later. Okay, so we're going to be considering a particular setting for reinforcement learning. There are various settings which are slightly different optimization problems that you might want to solve, given a Markov decision process. So in the episodic setting, the agent's experience is broken up into a sequence of episodes. And what is an episode? So in each episode, you first sample an initial state from this initial state distribution mu, and then let's see. Okay, I'm going to show on the next slide what this process is, but a process of generating actions and then getting states and rewards continues until you reach a terminal state. So this loop involving the agent and the environment goes until you reach a terminal state. And that means that, there's a certain state in the state space which is designated as the terminal state, and once you get there, you're stuck there, and you get 0 reward. There's several different kinds of problems this might correspond to. So you can have problems where termination is good and you want to finish some task as fast as possible. So let's say you've got a taxi robot and you want it to reach its destination and it gets a reward when it gets there. So then termination is good. Or you could have maybe some kind of, you could have a fixed length episode and then termination always happens after, say, 1,000 time steps. Or you could have termination being bad, like you're trying to get a robot to walk, and if it falls over, then the episode terminates. Okay, in this episodic setting, the goal is to maximize the expected reward per episode. So this is actually kind of the reason this is non-trivial, and the reason I had to go to the trouble of talking about the episodic setting, is that people sometimes define other optimization problems. For example, you want to optimize the reward averaged over time steps. So sometimes people consider just one really long chain of experience. So you never end episodes and reset the state, and then you're just trying to maximize expected reward. So we're not going to consider that setting. We're going to use this episodic setting. Okay, so the other thing that I'm going to need to define is the policy. So there are two kinds of policies we care about. Deterministic policies, where the action is a deterministic function of the state, and stochastic policies, where the policy defines a conditional probability distribution over actions, so probability of action given state. And the policy is going to be the thing that we optimize. Okay, and we can talk abstractly about a policy, which is just a function or a probability distribution, but or we could talk about a parameterized policy, where we assume there's some parameter vector theta which indexes over policies, and this is just a vector of real numbers. So then, when we set it up that way, then we just have some optimization problem over theta. Okay, any questions so far?
In the stochastic policy, for example, the actual reward that you have at the given state, do you consider this part of the state, or it has no influence whatsoever in the choice of action?
So, in the definition of the MDP that I'm giving here, the reward could depend on the action. So here, the reward could also, it could be random. So you're just sampling reward at next state, given action and current state. So everyone defines reward in a different way, or everyone defines the MDP in a different way. Some people call the reward a function of the state, some people call it a function of state and action. These things are all actually equivalent because you can always, given an MDP that's defined in one way, you can always construct an MDP that satisfies the other definition that's equivalent. So, but in this case, I'm allowing for the possibility that the reward is random and depends on the action. Okay, so here's what this all looks like mathematically. So we sample our first state, then we sample our first action given the first state, then we have a transition, next state and first reward. Then we sample next action, next transition, then last action, and then finally we reach this state called S sub t, which just so happens to be a terminal state, meaning the episode is done. And then we add up all these rewards, R0 to R sub t minus 1, and that's what we're trying to maximize, the sum of all these rewards. Questions? Okay, so, and you can also draw it as a graphical model like this. Okay, so, oops, I already told you what parameterized policies are. Okay, so the parameterized policies are, so it's this family of policies that's indexed by a parameter vector, theta. They could be deterministic or stochastic. I'm going to just write theta as another argument to these functions, or another variable that you're conditioning on. Okay, and you might ask, okay, so how do I actually define a parameterized policy concretely? so how do I, like, let's say I'm trying to implement an RL algorithm. How do I define how do I actually code up my policy? So it's just the same thing you would do if you're doing classification or regression. So for example, if you have a discrete action space, meaning that your action space is just a finite set, then you can just define a neural network that outputs a vector of probabilities. The same way you would do if you're defining a classifier. And let's say you have a continuous action space. So let's say your action space is a vector of real numbers. Then you could just have the network output the mean of a Gaussian distribution and a vector which is the diagonal of a covariance matrix. So that way, this is how you can define stochastic policies for a discrete or a continuous action space. And you can, for deterministic policies, it's even simpler. Okay, so now I'm going to start talking about how to actually solve the policy optimization problem. And so the problem we're trying to solve is we're trying to maximize the expected reward, and I'm just writing given, I'm just using this notation to mean that we have a policy pi, which has parameter vector theta, and we're using that to generate a trajectory. And so we care about this expected reward. So that's our objective function. And so the derivative-free optimization approach just looks at this as a black box where you put in theta and then something complicated happens, and including noise, and then out comes the total reward of the episode. So we're just viewing this as a black box, and the only way to actually optimize theta here, since we have no idea what's going on in the black box, is just to try out lots of different thetas, and some of them look better than others, so we just move towards the good ones. Okay, so we're ignoring all information other than R collected in the episode. Right? That's the black box approach. Okay, so I'm going to talk about a particular black box optimization approach called the cross-entropy method. And this is called an evolutionary algorithm because at every point in time, it's maintaining a distribution over parameter vectors. So that's kind of like if you have a population of individuals, and some of them have higher fitness than others, so you make those ones reproduce more. And your distribution moves towards the individuals with higher fitness. So it's called an evolutionary algorithm, but it's not going to involve anything like mating or something like that, or it's just going to have Gaussian distributions. So it works embarrassingly well, and whoops, that didn't come out very well. So there's a table. So this table is showing the performance of various algorithms on the. Let me get my mic. You can hear me fine, right? This one, testing. 1, 2, okay. Okay, unfortunately the table didn't come out properly, but so basically this is comparing a whole bunch of different reinforcement learning and non-reinforcement learning algorithms on the task of Tetris. So Tetris has been used as a benchmark task in reinforcement learning for decades. And I mean, for example, Dmitry Bertseikas, who's one of the big names in the field, he uses Tetris in a bunch of his papers and shows how these different approximate dynamic programming algorithms do on Tetris. So the thing is, these kind of reinforcement learning algorithms get scores around 5,000, 10,000. That's how many lines you clear in the game of Tetris. And then, so cross-entropy method and related evolutionary algorithms have scores that are like 2 orders of magnitude larger. So they get scores in the millions. And well, the reason is actually that, I mean, it's not too hard to explain. It's because those methods are actually optimizing the thing you care about, which is your final score in the game of Tetris, whereas the reinforcement learning methods are making some assumptions, like they're introducing time time horizons and stuff. So there are little errors that cause the reinforcement learning to not do exactly the right thing. And that means that reinforcement learning sort of plateaus at a fairly bad score, whereas the evolutionary algorithms get to an extremely high score. So that's why it's kind of embarrassing how well it works, because it's a benchmark for reinforcement learning, but these non-reinforcement learning algorithms do a lot better. I actually don't view it as that embarrassing because, so the problem is, they're like, this problem has like 40 parameters, the way it's usually defined. So it's usually defined in terms of, like you have 40 features of the Tetris screen, and you're just learning a linear function of those features to define the policy. And so if you have 40 parameters, then a derivative-free optimization algorithm is totally fine. It'll just crush that problem. I mean, the problem is derivative-free optimization algorithms don't scale that well to very large number of parameters, like millions of parameters. So you're not going to use it to optimize a big neural net, like a really big neural network. But yeah, I don't think you're going to do any better with actual reinforcement learning on this problem because you have so few parameters. But anyway, okay, so that's a good paper for that. So then, actually there's a paper at NIPS a couple years ago that I liked a lot, called Approximate Dynamic Programming Finally Performs Well in the Game of Tetris. So they actually were able to get as high of a score using a RL algorithm as you can get with cross-entropy method. But it's still a little disappointing that with a much more complicated algorithm that uses much more information about the problem, you're still kind of just barely catching up to this method. Okay, and also in terms of working embarrassingly well, so there's this other very closely related algorithm called covariance matrix adaptation, which is basically cross-entropy method that's souped up in a few ways, just a few, it's sort of a few heuristic ways that make it work a little better on certain problems. And this is actually very popular in graphics. So you'll see, like at every SIG graph, there's papers about using CMA to optimize different kinds of things. For example, people have been using them to optimize locomotion controllers of characters. And so there are a couple. These are a couple papers that do that. The point is they're still optimizing fairly low-dimensional policies, though, like less than 100 parameters. So that's where these methods work really well. Well, anyway, without further ado, here's the actual algorithm. So you first initialize the mean and standard deviation of all your parameters. So what does that mean? So at any given time in this algorithm, we're going to keep track of a Gaussian distribution over candidate parameter vectors, right? So because this sort of smooths out the problem. So instead of just having one current iterate, we have a whole distribution. We're going to try to move the distribution to the good part of parameter space. So every iteration, so we start off with a mean and a means and standard deviations. And every iteration, sorry, it got cut off a little bit. There's supposed to be a for loop here. This should say for iteration equals 1 to ... First we collect a bunch of different parameter vectors, a bunch of different random parameter vectors sampled from this distribution. So this is our population. Then we just, for each parameter vector, we just get a noisy performance evaluation of it. So each parameter gives us a reward. Then we just take the top 20% or top P percent, and we call this the elite set. So these are like the individuals with high fitness in the evolutionary parlance. And then we just fit a new distribution to the elite set. So we just update the mean and the covariance to maximize likelihood of the elite set. So this is just ridiculously simple, right? And then at the end, your best parameter vector is just the mean of that distribution. Okay, and so it's pretty clear why this algorithm works. So it's not that, so maybe it doesn't need analysis that much, but you can still analyze it anyway. And it's actually kind of hard to analyze the cross-entropy method itself. And actually, there will be one of the problems in the list of exercises talks a little about why. But it's kind of hard to analyze, but there's actually a closely related algorithm that's much easier to analyze and ends up being a minorization maximization algorithm, which monotonically increases expected reward. So I won't go into details here because it would require a kind of long tangent, but if you're familiar with the Monte Carlo EM algorithm, so recall that this algorithm works by, it collects a bunch of samples and then you reweight them to get a distribution of your, it's giving you a distribution over your latent variables when you reweight your samples, and then you maximize the likelihood of those samples. So it turns out that there's a, so let's see, here's, if what you do every iteration is you maximize log probability of your parameter vector times the reward obtained from that parameter vector. So if this is the objective you maximize each iteration, then it ends up being a lot like the Monte Carlo EM algorithm, and it has a, well, it's a minorization maximum, I should say, oh yeah, this is right, minorization maximization, and it has a, you can actually get monotonic improvement of the expected reward. Okay, so that's all I have to say about the cross-entropy method. Any questions?
Before running the cross-entropy method, you have to learn the policies. This has to be prefix or something like that.
Sorry, I didn't understand.
I mean, before running this method, you need to specify how to move from parameter to reward.
Oh, yeah, that's exactly right. Yeah, so this assumes that theta is the parameter vector for a policy. So for example, let's say you have a neural network which defines a policy. Then theta could be formed by just taking all the weight matrices and all the biases and concatenating them together into a long vector. So you just, it's just the parameter vector for the policy. Other questions? All right, okay, so now I'm going to move on. Oh, actually, so now at this point I want to stop lecturing because no one wants to hear me talk for 3 hours in a row, and point you to the exercises for the cross-entropy method. So I'll show you what they look like. So let me just show you the link again, in case you didn't get it. Oops. Okay, so here's the link. So if you go to that website, oops. Oh, I don't have internet on this computer.
The link is on the MLSS website as well, so they can go to the...
Okay, great. So there's also a link on the MLSS website. Oh, actually, I am on the internet. Great. Okay, so it just has these two links. So if you click on this link called Lab 1, so there's a few problems. One is to implement the cross-entropy method and run it on some very simple control tasks. And I've provided some starter code for doing this. So actually you don't need to write very much code. You only have to write like 4 lines of code. Yeah, so most of the code is here. Then you'll finish writing the algorithm, and then it should do something. Well, actually, I want to attempt a live demo because those never work. But you should see something cool happen, like a pole balancing on a car. One of these, I mean, there are a bunch of these classic control tasks which are used in the RL literature, and you can use those. Okay, by the way, this is using OpenAI Gym. So that's what some of my colleagues and I at OpenAI have been working on for last few months. So basically what this is it's a set of environments, well, it's a set of reinforcement learning tasks, and made to be like very standardized, so you can compare results, and very easy to get up and running with. So it's really easy to install. You can easily, so these are the instructions. You can even shorten this by just doing pip install gym. But I don't like telling people to do that because I'd rather if you actually download the code so you can look at it, and in case you run into some kind of problem. But you can just do pip install gym and that should also work. So anyway, once you get it installed, then you have all these environments available, like the cart pole and the pendulum and so forth. And then you can start writing reinforcement learning algorithms. So anyway, that's the first problem. And then there's a second problem that's about analyzing cross-entropy method, which is possibly a little hard. Well, I don't, hopefully it makes sense. And if it doesn't make sense, just ask me about it. Let's see. Okay, and that's it. So I'll, let's see. This should, I don't know how long this is going to take, but I'll just try to get, let's just say 45 minutes or an hour, and that'll be the working assumption, but maybe everyone's already, yeah, let's say an hour, because there's, like once you get cross-entropy to work by writing the relevant lines of codes, there are all sorts of other things to try, because it's not going to work on everything. So you might as well try some other stuff. So let's reconvene in, let's reconvene at 11. And I'll be around here, so if you want to ask me questions, please do so.
Well, thanks for the question.
Let's see my notes. It's probably I have it.
You were there.
Yeah.
Yeah, I saw the error.